So in this video, we'll talk about a problem from an old AP exam for Calc BC. It's from 2007. It's problem number 3. This was a calculator problem that dealt with some polar coordinates. And they gave us two polar curves to start things out. They gave us the polar curve r equals 2. So that's this polar curve where the radius is constant. So we end up with a circle of radius 2. And then we also have r equals 3 plus 2 cosine of theta, which traces out the limacone that you see here. We're told where the intersection points are, so that's kind of nice. They tell us this intersection point is at 2 pi by 3, and then this intersection point is at the theta value of 4 pi by 3. In part A, we're asked to find the area of region R, and if you notice where region R is inside the graph of r equals 2, but also inside the graph of the limacone over in the second and third quadrants here. So to find the area of the shaded region, the approach that I chose to take was I chose to kind of break the area into two pieces. I realized this sector right here was a sector of a circle, and I can find the area of a sector of a circle pretty easily using 1/2 times my angle times my radius squared. So the only thing that I had to make sure I did properly was I had to make sure I found what the angle within this sector of the circle was that I actually wanted the area of. And so if you think about the full number of radians within a circle, it's 2 pi radians. Now I knew I didn't want to account for this number of radians, this little wedge that's kind of broken out of the circle. And so what I did is I figured out what the difference between this angle right here and this angle right here were, right? And we're told what those angles were. 4 pi by 3 is the one that's down in the third quadrant. 2 pi by 3 is the one that's up here in the second quadrant. If we do 4 pi by 3 minus 2 pi by 3, we've already got the common denominator. So the portion of the circle that's poked out right here is 2 pi by 3 radians worth. And so I just took the full 2 pi radians of the circle minus the 2 pi by 3 times the radius squared. This computation right here is going to give me the area of the sector of the circle that I have in blue here. Now I also need to account for the area that I kind of outlined in red over here. Now that's going to be a little bit trickier to handle because this is not circular right here on this little wavy portion of the limacone. And so what we're going to have to do is we're going to have to take one little slice of that region that originates at the origin. And if we approximate this little wedge of the region to be a sector, we can approximate its area with 1/2 times some tiny change in theta, so delta theta, times whatever the radius is squared. Now, this is why it's an approximation. The radius is not constant from the origin out to this little stretch of the graph right here. And so we're approximating this area as if it were a sector. We know that this portion of the graph is traced out by r equals 3 plus 2 cosine of theta. So if I put that in place of my r, and we'll realize that I don't just want the area of this one little portion of that region, I want the area of the whole entire shape that's outlined in red right here. I'm going to use a definite integral as a means of adding together a bunch of these small sectors areas. And so if I integrate this expression in its limiting form, the delta theta becomes a d theta. And then my limits of integration, what angles do I range between? What values of theta do my angles range between to get from this portion on my limacone to this portion right here on my limacone? Well, that goes from intersection point to intersection point, and we know those are 2 pi by 3 and 4 pi by 3, so they don't even make us work for them. To conclude, I just had to total those individual areas that I did in red and blue here, so I did everything on the calculator. No sense in trying to evaluate this by hand if the calculator's in play. And what I ended up with was a little bit over 10 square units. In part B, they ask us to do something that's a little bit different. They're telling us that there's actually going to be a particle with non-zero velocity that's going to move along the limacone, right? So it's going to move along the outer polar curve here, which becomes the inner polar curve for that little stretch in the second and third quadrants. And the position of the particle is given by x of t, y of t at any time t, and theta is equal to 0 and t is equal to 0. So basically that means that theta and t are kind of synced up with each other. And we're also told that the particle is going to move along the curve so that the rate of change of the radius between the particle and the origin over time is equal to the rate of change of the radius of the particle with respect to the angle theta. So what we're asked to do is we're asked to find dr dt at theta equals pi by 3 and then try to interpret what that means as far as the motion of the particle is concerned. And so the first thing that you can do here, because they tell you that dr dt is equal to dr d theta, you know that r as a function of theta is just the equation of that limacone. And so if you take the equation of that limacone and you just do the derivative of it on both sides with respect to theta, what you end up with is the 3 dropping off, and then the 2 is going to get copied into your derivative, but then the derivative of cosine of theta with respect to theta is going to be negative sine of theta. So here's dr d theta, and since dr dt is equal to dr d theta, that implies dr dt is equal to negative 2 sine of t. Well, we wanted to know what dr dt evaluated at pi by 3 was, and so that's going to correspond to dr d theta evaluated at pi by 3. And so when we put pi by 3 into our formula for dr dt or dr d theta, they're the same, so whichever you want to do is fine. We end up with sine of pi by 3. Now you probably know sine of pi by 3 or have a means of figuring it out without a calculator. The calculator's in play here, so we could represent this as negative root 3 if we cancel these 2's, or we could just toss it into the calculator and we end up with negative 1.732 rounded to 3 digits of accuracy. But then it goes on to say we want to interpret what this result means in terms of the motion of the particle. And so I looked at this as the rate of change of the radius with respect to time. And so what I said was the rate of change of that radius of the path of the particle with respect to time is negative. And that's going to indicate that the distance between the particle and the origin is decreasing by 1.732 units distance per unit time at the time of pi by 3. And so the only other thing that I had to kind of think about was what was going on with my radius, because if my radius is negative and it's decreasing over time, it's becoming more negative, so it's actually becoming a smaller numerical value. But if you think about it, we're dealing with a positive radius up here, and you can kind of prove that by putting pi by 3 in place of this theta in the formula for r of theta. And so since r is positive at pi by 3 and the rate of change is negative of r with respect to time, we know the particle is getting closer to the origin at this time rather than further away. Part C is kind of a continuation of Part B. It's talking about the same particle, and now they're concerned with the y rate of change, right? The rate of change of y with respect to time is equivalent to dy d theta. So again, t and theta are pretty much synced up for us here. And they ask us to find the value of dy dt at the instant time when theta is equal to pi by 3, and then interpret what that means in terms of the motion of the particle once again. And so if we know about the relationship between y, r, and theta, which is just the relationship that you would normally use going between polar form and rectangular form, and we know that on this path, r is equal to the equation of the limacone, 3 plus 2 cosine of theta, we have a relationship between y and theta that can be established pretty easily. Now, since dy dt is equivalent to dy d theta, we can go ahead and just take the derivative of this with respect to theta. Now I went ahead and used a product rule. So I took the derivative of this first times the original second piece. Original first piece is what you see next after I've added on, and then times the derivative of sine of theta to finish that off. Well, dy dt is going to be this exact thing, but with t in place of the thetas. And so then if you go ahead and you evaluate that at pi by 3, since that's one more time what they ask us to do, I didn't try to evaluate this by hand just due to all of the t's or all of the thetas that you'd have to put pi by 3 in for. And so I just evaluated this on the calculator and I got positive 1/2. And so one more time we have to try to interpret what this means in terms of the motion of the particle. And so once again, I looked at dy dt to kind of arrive at this interpretation. So since the rate of change of the y coordinate of the particle over time is positive, the y coordinate of the particle is increasing by 0.5 units distance per unit time at this time. Now, that's just kind of the general interpretation of this. It doesn't really have to do with the motion of the particle. Which direction is the particle moving in the y direction? Well, what I did is I kind of looked at my graph, and I have the point 4 comma pi by 3 up here toward the peak of the limacone. My particle is going to be increasing for just a tiny bit more. It's not increasing quickly, right? But the y-coordinate of the particle is increasing by 0.5 units distance per unit time at this time. So we're almost done increasing with our y-coordinate. We're about to the peak that's, you know, up in here somewhere, and we're going to start decreasing. But at this moment in time, since the y-coordinate's positive and the rate of change of the y-coordinate's positive, we know the particle is moving upward at this moment in time.